Okay, so as I was saying, in the DevOps world, challenges often reveal themselves in unexpected ways. Through our session, we would share our team's journey in addressing intricate complexities in cloud scaling. We would share a lot of issues that we encountered, like 503 errors, Kubernetes increased latency, and other service mesh intricacies. Our story isn't just about problems, but a testament to the adaptability and resilience of DevOps in surmounting unexpected complexities. So this is the agenda for today. We're going to talk about Kubernetes scaling, a lot of bottlenecks that we faced and tackled along our way, and we would share a lot of strategies of how you can improve the performance of your cluster. So we'd be open to questions at the end or even after the session. All right, let's start. Over time, number of application workload grows in your cluster. So with an increasing number of pods and application, cluster services like core DNS, kube proxy would need to be scaled because they would need to support the increasing application workload in your cluster. So you can either opt for horizontal or vertical scaling. Now, as application and core services are increasing, the cluster data plane that is hosting all these applications would also need to be scaled. In our case, we use Cluster Autoscaler or Carpenter to scale the Kubernetes data plane. Now, as the data plane increases, number of nodes, daemon sets, and other stuff would need to be supported, and we would need to scale Kubernetes control plane for that. Now, scaling of Kubernetes control plane would depend on the cloud provider you have and the kind of Kubernetes setup you have. But I just want to emphasize on this that it is a very critical component, and you should implement scaling for control plane as well. Now, the performance impact of a slow Kubernetes API server can be very significant. It can affect the overall stability and responsiveness of your Kubernetes cluster. The API server is a critical component for your cluster, as it serves as the entry point for all your API requests, and it manages the state of your cluster. So when it becomes slow or unresponsive, there can be various issues. Some of them are listed here that we faced and tackled along our way. Slow API server responses can cause delays in creating, updating, or even deleting the resources within the cluster. This can impact the agility and responsiveness of your cluster. Now, application and tools that connect with the API server like kubectl or any other custom controller that will experience increased latency in their operation as well. That would lead to slower application development and management. Now, slow API server can also be a bottleneck for resource utilization in your control plane components that can lead to resource contention and including high memory or CPU usage. Then next we have the, while we are scaling the cluster, I think there's some extra text box that has been added, so apologies for that. Scaling the cluster may be hindered by a slow API server. It can impact the ability to schedule new nodes or pods in a timely fashion. Then scaling up or down too rapidly as well can impact Istio's ability to efficiently propagate the changes across the service mesh. In our experiments, we noticed a direct correlation between scaling speed and a lot of issues like 503 errors. In large clusters, slow service mesh performance leads to stale configurations. During one of our major incidents, service mesh was routing traffic to a shutdown application for 12 minutes. So you can imagine what kind of revenue loss that can cause. So we'll talk about Kubernetes scaling and some performance bottlenecks. When we talk about scaling application, it is not just about increasing the number of pods. It's a delicate dance between resources and configurations that can impact the responsiveness of your cluster. Number one, we have the API server. It can become a bottleneck, especially in clusters with high number of API requests. How you can mitigate this is you can implement horizontal scaling, or you can use caching mechanisms like client-side or server-side caching. The control plane components like HCD, Cube Scheduler, or Cube Controller Manager, they may experience scalability issues as your cluster grows. How you can mitigate that? You can ensure that these components are properly sized. You can use custom resource quotas and limits to manage your resources. Next, we have the misconfigured service mesh. It can put a lot of unnecessary load on your Kubernetes control plane and increase the overall application and cluster latency. How you can mitigate that? Implement cluster autoscaler. You can also consider using node pools to define different sets of instance type to be used. Lastly, we have the high rate of pods and nodes churn within the cluster, which can decrease the overall performance and scalability of your cluster. You should, or I would say you must, implement well-defined naming conventions and service labeling for that. One more bottleneck which is not added over here but I would like to emphasize on is inefficiently designed and resource-hungry applications that can strain the cluster when scaled. You can leverage the Kubernetes vertical pod autoscaler for that to adjust the resource request and limits for the pods dynamically. Now I'm going to deep dive into some of these bottlenecks and how we address them. I call this section as Unveiling the Hidden Challenges. Hidden because even with the best of DevOps professionals, when you're working on large-scale clusters, a lot of small configurations go unnoticed. And that happened with us. And if, that's why I call them hidden. And if even a few of them are helpful to you as well, that would solve our purpose. So I'll first deep dive into the API server bottlenecks. As I said earlier, it is a very critical component of the Kubernetes cluster. So here are some of the Kubernetes API server performance bottlenecks, and I'm going to share how we addressed each of them. A high volume of incoming API requests can overwhelm the API server and lead to performance degradation. How you can mitigate that is, number one, implement horizontal scaling by running the API server instances behind a load balancer to distribute the request load. You can use rate limiting and request throttling to manage incoming traffic and prevent overloads. Next, we have the authentication and authorization delays. So when the auth processes are slow, it can delay the API responses, especially in environments with complex or slow identity providers. Now, you can implement efficient auth mechanisms and consider caching and access control policies to reduce the latency. You should also use identity providers that are optimized for speed and reliability. Now, long-running API requests can hold resources and connections, leading to delayed response for other requests. Now, you should implement request timeouts and connection timeouts to limit the duration of long-running requests. You can use control mechanisms to enforce resource limits for your API request. Next we have is the inefficient queries. The complex or inefficient queries like list requests with extensive filtering that can consume excessive resources, and it can slow down the API server. So what you can do is you can optimize your client queries to minimize the amount of data that is being filtered and only take up the necessary information. Again, you can leverage the caching mechanisms and client-side optimization for your queries. Next, we have resource constraints. So inadequate CPU, memory, or network resources can limit the API server ability to process the request. You can allocate sufficient resources to the API server pods, obviously considering the size and demand of your cluster. Monitoring is the key, and I cannot emphasize enough on this. So do monitor resource utilization and adjust the resource request and limits as required. Lastly, we have the admission controllers. So overuse of admission controllers can introduce delays in request processing. So you should review and optimize the use of them. you can disable or reduce the use of controllers that are not essential. As Floor said in her presentation, spring cleaning, I would say Diwali cleanup for us, for our clusters, that you should definitely implement. So next we'll talk about control plane bottlenecks. Control plane is again a very critical component responsible for managing and maintaining the cluster's overall state. So performance bottlenecks in the control plane can significantly impact the reliability of your Kubernetes cluster. Let's talk in detail about some of these. Node failures and the subsequent rescheduling of your pods can put additional load on kubeproxy as it updates rules for the new pod locations. How you can mitigate that is use readiness probes, liveliness probes, and in your application's pod specifications to detect and handle the pod failures. Now you can also employ resiliency mechanisms like PDBs. PDB is pod distribution budgets to control the rate of disruption during node maintenance. Next we have is the CoreDNS and kubeproxy scaling. If your cluster experiences significant growth in the number of pods and services, kubeproxy may require scaling to handle the increased load. What you can do is you can deploy kubeproxy instances on dedicated nodes to distribute the load. Next we have is the inadequate resource allocation. The CPU and memory resources that are allocated to CoreDNS pods can lead to slow performance. Now you should adjust the request and limits for CoreDNS pods, very basic. Again, monitor the CoreDNS resource utilization and adjust the resource allocations as required. Next is very basic, but we often miss it. The choice of EC2 instance type for worker nodes can affect the overall network performance. So choose the EC2 instance type very wisely, monitor the network performance, and consider upgrading to or switching to another instance type as required. Next we have the CNI plugins. The choice of container network interface plugins can impact kubeproxy's overall performance because some plugins may be more resource intensive or less efficient. You should evaluate and choose a CNI plugin that is well suited for your cluster specific requirements and performance considerations. Regularly update your CNI plugins because you can leverage from the bug fixes or the improvements that come along the way. Lastly, we have running unnecessary daemon sets. Again, Diwali cleanup. Running unnecessary daemon sets in large clusters can cause a large number of unnecessary pods to spin up. Now, scaling is not just about applications. It has a profound impact on the core components as well. So, in one instance in our production cluster, where it faced degradation because of the number of pods reached 30,000 with 3,000 nodes. So, the root cause was an excessive number of daemon sets that largely attributed to an accumulation of small size nodes over time. So the last bottleneck that I would like to discuss is service mesh misconfiguration that we often miss because of the little details. Number one, I would like to talk about running unnecessary services as part of the mesh. This is the most common misconfiguration that happens. Generally, we tend to deploy services with Istio sidecar and make them part of the service mesh. This increases unnecessary burden on the Istio control plane. So, and it would contribute to the latency in the application traffic as well. Next, if we don't configure the rate limiting and connection pooling, in some scenarios, services can throttle the Istio control plane. And that would, in the end, result in poor performance of Istio. Then we have resource limits. Not properly configuring your resource limits for your Istio components can lead to resource exhaustion and performance problems. Lastly, we have uncontrolled configuration sharing across namespaces. So you can define virtual services, destination rules, or service entries in one namespace and then reuse them in another namespace. Istio exports all traffic management resources to all namespaces by default. But you can override the visibility with the export to field that would help you to control which namespace can access and reuse these Istio resources. Now to continue talking about Istio and a lot more, I would hand it over to Rajat.
Thank you, Anchal, and thank you so much for explaining all the bottlenecks of Kubernetes control planes, API server in an efficient way and how we can mitigate them. So just continuing from the last slide, like we Anchal already discussed about the misconfigurations that generally people is having in during like while they set up the service mesh and when they deploy the applications. So we also did the same mistake. We follow the same misconfigurations, and somehow these misconfigurations ended up a very big revenue loss for us and a lot of application downtime for us. Now I'll discuss what are the different factors with this misconfigurations that led us to that downtime, for the application downtime. So with Istio, if I talk about not just Istio, but any service mesh generally works. However, it basically it deploys some proxies across all the sidecars in your containers or pods, and these sidecars basically look the events of the clusters. So control plane or Istio or service mesh control plane is responsible for updating all the events and pushing those config to the sidecars. So what happens if there is any latency from the API server side or control plane side, the push or the push of events or the push of configurations can be delayed. And this delay can cause a lot of revenue loss, not because when you there's a delay in push, so what can happen, your Istio or a service mesh can send the traffic to the pods that are actually not available. That has been down because of the scaling and something, but Istio is still sending the application traffic to them. So what are the different regions that can delay to this push configuration? So one of the thing is larger configuration. So as I told, like we were running our cluster at very large scale. So there were around 30K pods and more than around 2,500 nodes in the cluster. So the size of configuration is very large. So any change or if any pod is going down, so there will be around 2,500 something site proxies, and we have to push all those config changes to all the pods. So this led us to a very larger size of push config changes in the Istio mesh. The next thing is the rate of the high rates of basically the change rates, how frequently the events are getting triggered. So when we were running with that very large scale, so any deployment, like a simple deployment which is running around 1,000 pods or more than 1,000 pods. So whenever new deployment comes, we have to scale down 1,000 pods, and again the new 1,000 pods will come up. So with this rate, the number of events will trigger a lot, and this will eventually increase the load on Istio control plane and eventually delay the whole process. The last thing is the resources on the service mesh. So basically, when you plan your cluster for the application, you define some resource request and the limits for your Istio or whatever the applications you are deploying. But over the time, Istio is just something like it is a part of service mesh, Istio service mesh, and all applications coming into cluster are getting as a part of the service mesh. So they overall increase the load on the service mesh. So if you don't monitor, or I'll say if you don't vertically scale all the resources on the control plane, it might impact in terms of performance and everything. And even though Istio or other service mesh does not scale horizontally really well, like if you talk about the Istio, any open connections will remain open until they're, like even if we are scaling horizontally, the connections which are exist earlier will remain open until they are not closed. So they are not going to be spread over across all the pods, even new pods are coming. So this was one of the challenge with the Istio, and the last is workload distribution. So with the workload distribution, when we talk about the workload distribution, when we deploy applications, we define lot of constraints like a pod constraint, pod NT-affinity, pod topology constraint, and all those stuff. So with these constraints, we can end up having spin up larger number of nodes that we don't need actually. So with this constraint, so these are the different regions. We see a larger scale in these factors come into play for our clusters, and overall degraded our performance in the service mesh. The next thing is what was the impact? I just earlier explained. When there is any event change in the cluster side or in the Kubernetes API server, Istio or service mesh control plane is responsible for pushing those config to do all the pods or all the proxies. So once there is delay, let's say if API server performance is not good, so what will happen? There will be delay from the API server side from the sending that event or particular pod event or whatever event. So it can. So this is the first delay. The next is if the Istio control plane performance is not good, there will be another delay from the Istio side to send the latest update to all the proxies. So these delay can cause, like this delay can be up to 1 minute or can up to 10 minutes, depending on the configuration and the performance of your cluster. And this can be a lot of, like this delay, like if the delay is very high, it can increase 500 errors or like something else. So this happens with us, like the delay was around 10 to 12 minutes, and somehow for 10 minutes, if the pod is getting down, the Istio or service mesh was not able to basically remove those endpoints from the service mesh, and the load was still, traffic was still going to those pods. So for these issues, we have basically done some profiling on the Istio side. We fixed some issues from the Istio open source, and overall improve the performance. But yeah, these changes or factors can cause a lot of application downtime and the cluster instability. So in the world of DevOps, every challenge is opportunity to learn and grow. So for us, this downtime or this application revenue losses was a huge opportunity for us to focus on the reliability and stability of our system, because we were growing at very large scale. Our clusters were having more than around 3,000 services, and clusters like nodes were getting increased day by day. Like eventually we reached up to 3,000 nodes. That was not, like that is very high scale if you running application or production workload. So we have basically implemented some strategies for smarter scaling so that we can reduce this number of workload from the clusters. Apart from that, we can remove all those bottlenecks that we have earlier, that Anchal explained earlier, and so that we do not face the same downtime for our application and the production loss. So what we did for this, sorry. So we did on the control plane side, actually we were using one of the cloud provider, but even for the cloud provider, we can do something for us, like control plane components like QProxy and core DNS are actually run in our infrastructure and managed by our team. So what happens, we did basically limit workload and node busting. So what this mean basically, sorry. So when the cluster is grows, like all the core components like core DNS and QProxy does not grow by itself. You have to configure the auto scaling, and sometimes auto scaling is not very much good in terms of if you are running like more than 3,000 nodes. So what we did basically for core DNS, we implemented the local node cache DNS. So that was the solution for us so that we can reduce the load from the API server on the control plane and can improve overall performance. The next thing is replace long running instances. So if any instance is running more than, I'll say 5 days or more than, like running from the very long time, what can happen? There can be multiple things happening under the nodes which are not very visible to containers. And this can, like there can be services or daemons which are not performing well and can reduce the overall performance of node. And eventually this will reduce the overall performance of the containers. So we maintained, we are basically, now we are replacing all the instances in every 5 days in a step-wise scaling. We are not running like any instance more than 5 to 10 days. And we are upgrading AMI as well with this rollout. The next thing is client-side cache. So there were applications, there were several applications in our clusters basically that were directly calling the EKS API or like Kubernetes API. So we, for those applications, we gathered the development team and we asked them to to utilize the caching for them. So with this cache, we have reduced a lot of load from the control plane, and somehow this have increased the performance for us. And the next is, even for as a developers or as a admin team, what we do, we generally perform kubectl commands on the cluster and try to find resources via kubectl, and we do a lot of things. So what happens in very large clusters, if you're running 30K pods or more than 30K pods, running a single kubectl get pod command is very load or resource intensive. So you have to make sure once you are running this command, you must be running like in a caching enabled way, or you should be scaling. If you are running one time, you should be make sure you are not running any complex query, which is basically even more heavy, more loading the Cube API server and exhausting the resources. The last thing is disable API necessary. Sorry, I missed just one thing. Auto scaling DNS. I already discussed in like what we did instead of auto scaling, we went with the node local cache DNS. So this improved a lot for us. And the last thing is disable any unnecessary API server extension. So there are a lot of API server extension that we can like. There are a lot of operators and controllers that we build in house. We adopt from the open source, and there are certain extension we actually used to prefer to implement them rather than we utilize them. So I can give you one of the example. Sorry. So we were using EFS drivers or like other CSI drivers. There were multiple drivers, and all the applications were not using like just using one drivers, and we were installing 3 different drivers. And those drivers, as a Damon said, so those were basically loading a lot of API server resources and causing a lot of queries on the API server and causing a whole lot like different loads on the API server and control plane. So those were basically involving in the like contributing in the slowness of the performance. The next thing is data plane considerations that we have done to improve overall performance. The number of pod churn rate is very high for us. Basically, when you are running 30K pods, you have to make sure you are using canary deployment, or at least your scale down should be a step scaling. Scale up, scale down should be in stepwise. Otherwise, if it is happening in the burst mode, it can basically take a lot of resources from the API server and degrade the performance. So what we did, in every deployment, or even every HPA, we enabled the step scaling for the scaling up and scaling down. We enabled the step thing there. Another thing is, like we already told you, like we were running 3,000 nodes. So the another factor that was contributing to 3,000 nodes were the smaller size of nodes. So basically, there were some certain nodes with 2 CPU or some very less configurations. So this were basically contributing to a larger number of nodes in the cluster. So what we did, we just increase the size of the nodes, and eventually this decreases the overall number of nodes in the clusters. And when number of nodes goes down, it basically decreases the number of pods, basically the daemon set pods that were running in the cluster. So this was a huge reduction in terms of load on the API server. And then similarly, like the next thing is daemon set workload. So as soon as the nodes goes down, our daemon set pods goes down, and the overall loads decreases. The next thing is use compute resources efficiently. So when you deploy your applications, certain users try to give request. When they overcommit the request, the number of pods that can go to a node decreases, because Kubernetes can consider the pods on the basis of request. So we basically optimize all the applications in our cluster so that all the requests are basically in the permissible limit that is basically optimal way. And the last thing is basically we also updated the AMI. This is we used to do on a monthly basis, but now we are doing more frequently. And the last is disable unnecessary logging to disk. So there were certain applications which were using empty data to logging on the local disk. So that basically we have disabled this thing so that our node rotation can be easily driven. The last thing, we also did some more thing on the node side. So what we did, we have limit the node churn rate by, like, we have reduced the number of nodes. So this overall reduces the number of node churn rate for us. Apart from that, we have given some limitation on the services per namespace. We have basically modified our dynamic admission webhook. So basically, if I give one example for this, we were basically in the admission webhook, we were written some rule on the pod label. So if you are running 30K pods and if you are basically writing any keyboard or whatever rule on the pod level, so it can impact overall performance on the API server because admission is the API. It is directly related with the API server. So running a query on the 30K pods is quite difficult. So what we did instead of pod, we migrated to the controller level like deployment and stateful set. And the last thing we did basically used IPv6 for the pod networking because we were running this much of number of pods, and IPv4 is becomes like we have certain IP limitations, so we have to migrate to IPv6. I'll take so last thing like what we did on the service mesh side. So with service mesh side, we have enabled the auto scaling of the STO control plane. And apart from that, what we did, we moved a control plane to a separate infrastructure in the cluster, so that all other factors or application workloads should not impact this STO control plane. This is what we did just for the STO, so that STO cannot basically, the overall performance for the STO is good for us, and there should be no downtime or there should be no delay in the post updates. The last thing, like we have also did some configuration change in the STO, like number of services and all those things. We control the, we configure the rate limiting in the STO application, all the applications rate limiting and all those things. And the last thing is basically, even though applications were the part of service mesh, there is option you can remove their service endpoint from the service mesh. So we implemented those services which are not required the service mesh, we removed from the service entry for all those from them. So overall, so we have, we also, apart from that, we enabled proactive monitoring. We were doing the monitoring, but we went to the deep level monitoring for all those components so that we can avoid any future incidents. So overall, in our journey of this bottlenecks to how we migrated or how we scaled our clusters smoothly, we learned a lot of different things. We have shared what we have learned, what we have did. So I'll say DevOps is a learning journey where you can learn and you can see a lot of different challenges coming in your way when you scale or some certain things happen. So you have to adopt them, you have to migrate to a new technology or new strategy, I'll say, and you have to keep grow over the time. Yep, that's it from my side. Any questions? And yeah.
What kind of load testing simulations are you running to validate your optimizations?
Okay, so every application, like if you're talking about the workload or cluster applications, or talking about the customer or like user applications.
User applications specifically.
So I'll say it depends on the kind of application. An user application can be a data-driven application, or it can be a resource-intensive applications. So there are different tools available in the open source market, and they can basically use them. Apart from that, we have also given self-service portal to our users where they can run their applications in just a container level, and they can look for the resources, like how many resources getting just utilized. So accordingly, they can customize their resource request and all this stuff.
What would be interesting is to see how much of optimization or improvement that we have brought in after these best practices been implemented. So how do you measure it? Do you have any stability or performance index?
Yeah. So basically, if I give you a little bit figure what happens once we did all these migrations and all those things, we were running around 3K nodes and 30K something pods. And after all these optimizations, our workload decreases around, like right now we are running just 1,000 nodes and around 15K pods. So the overall, basically overall pods and resources is decreased by half. So this reduced us, like this basically helped us in the saving of the cloud and everything. Apart from that, once we have enabled all those things, we have basically created some performance metrics. And once we have measured those metrics and we have identified the delays that we were seeing earlier and latencies, that has been basically reduced drastically to 90% something. So that was the performance improvement that we have seen after these suggestions and all those things.
Okay, thank you.
Hey, here.
Yeah.
When you say you run 1,000 pods for some services, I just want to understand what type of workloads do you deploy that need 1,000 pods? I mean, what is the RPS for those services and all?
I'll say there are certain applications, and I'll say one of the applications like as a Expedia, we host different travel platform. So let's say Super Bowl is the event that is going on, like that is coming into next month. And at that time, we have a lot of traffic, and that traffic is like, we get around millions requests per second at that time. So we have to scale our workload or our applications to that, like 1,000 pods or more than 1,000 pods, I'll say, at that time.
Also, when you say 1,000 nodes in one cluster, why are you putting all of those in a single cluster? Why not have multiple clusters for that?
We have multi-cluster. We also have multi-clusters, but it depends on type of application and that data or that data they are going to host. We have certain, like if it is customer data or some users data, these are the critical things. So we don't, we plan accordingly, like we have certain PCI categories and all those stuffs come into picture then. So that's why it depends what kind of application application is going to serve. So it depends basically.